Even though light is a wave, in order to study light and how it acts in contact with different surfaces, for example, mirrors and lenses, we're going to treat light as a ray. A ray, mathematically, is just a line sort of originating from one point and carrying out. So we're going to model light just like that. We're going to imagine that light travels only in straight lines. So something like that, that's not light. Okay, everything is just going to travel in a nice straight line. So with reflection, we're thinking about a mirror, and then light coming into a mirror, and then bouncing off of it. For reflection, we're going to also want to consider a normal line, like this, and we're going to be measuring angles of reflection. Now, the rule, or law of reflection, if you will, is that the angle in, our incident angle, is always going to equal our refracted angle, or I'm sorry, reflected angle. So there's a very similar picture. We have our incident ray coming in, our reflected ray going out, and our two angles, and those two angles are always going to be equal no matter the surface. Now this is true even for things that aren't mirrored surfaces. For example, a rough surface looks something like this, where at each point, angle in still equals angle out, or incident still equals our reflected angle. But the normal, you'll notice, normal to the surface, right, 90 degrees to the surface, is pointing at a different direction for each little point that it hits. And so even though light's all coming in from the same direction, it's getting scattered multiple directions because it's hitting this rough surface. And that's why we don't always see reflections off of rough surfaces, is because this light is sort of scattering every direction and isn't always going, say, straight back to your eye like it would for a reflection. Refraction is something that occurs when light goes from one area to another. So let's imagine up here I have air, and below it water. When light goes from air into the water, it's actually going to cause it to bend a little bit. That's why, like, when you put a straw in a cup and you look at it from the side, it looks like the straw is sort of broken or bent, is because of this refraction. This occurs because of a difference in speed of light between the two media. So for example, air would be a faster speed of light and water would be slower. And so when you're traveling from one speed to another, it causes this bending of things, even things that want to travel in a straight line. So maybe kind of a little out there example is this. If I'm pushing a lawnmower and it's going from the faster sidewalk to the slower grass, what happens is as this starts to hit the grass, this very first wheel hits and goes slower than all the rest, and so the lawnmower begins to turn in this direction. And that's essentially what's happening with the water. As those waves are contacting that surface, the first part of the wave that contacts the surface is being slowed down more than the part of the wave that's out here, and so it starts to bend in that direction. An important thing when it comes to calculating these sorts of things is something called our index of refraction, which we'll use n for. So n is our index of refraction, and it's simply a ratio of the speed of light in that material compared to the speed of light in a vacuum. The equation to find index of refraction of any material is the speed of light, c, over whatever the velocity of light is through that particular medium, which is always going to be a little bit less than it is in the vacuum. A bigger number for n then means a slower material. Probably more useful to us is something called Snell's law, or our law of refraction. And that's going to allow us to actually calculate the angles involved, like theta 1 and theta 2 here, or our angles in here from our water to our air, our incident angle and our refracted angle. And what Snell's law says is that the index of refraction of material 1 times the sine of angle 1 is index of refraction of 2 times the sine of angle 2. And we can use that to figure out, if we know the angle that it goes in and we know the index of refraction of both materials, then we can figure out what the angle is that it is refracted at. Couple things to know, right? Going from fast to slow means we're bending towards that normal line, towards the perpendicular. If it's the opposite of that, let's say if we're going from the water, so there's going out of the water and into the air, we bend away from that normal. So there's our incident angle in our refracted angle. So fast to slow means towards the normal, slow to fast means away from the normal. And there's all kinds of applications for this. One very important application is total internal reflection. So let's say we have our material set up here, right? And if I'm going from slow to fast, so there's slow, there's fast here. If I'm going from slow to fast, I'm always bending away from the normal, so it looks something like that. Well, as I start to increase my angle of incidence here, as this angle gets bigger and bigger, so does this angle. And eventually you reach a point where there's your angle of incidence, your angle of refraction is 90 degrees. So theta r here would equal 90 degrees. When that happens, this light doesn't exit that material. It stays within that material. So when this happens, we call theta I the critical angle. So it's sort of what angle is needed to make our refracted angle 90 degrees. In other words, what prevents the light from actually leaving that material. One very important application of this is fiber optic cables. With fiber optic cables, every time we hit the surface here, so this is light traveling through a very small glass tube is essentially what a fiber optic cable is. The light travels through, and each surface it's going to hit it in such a way that it totally reflects inside. In other words, our refracted angle is 90 degrees. And so it's going to stay completely in that material. And so even around bends and curves and things, we can have light enter here, bend and curve around, and exit here, because every time it hits a surface, it's going to be totally reflected inside rather than refracted and allowed to leave the material. Dispersion is a concept that kind of explains how a prism works, or how we can separate white light or light of different wavelengths. So we have white light coming in, which is made up of the combination of all our visible light. When we hit this, we're going from air outside into glass. So we're going from a faster to a slower material, which means we're going to bend towards the normal. And again, here we're going to go from glass to air, so we're going to bend away from the normal. And you can kind of see that in the picture here. But what happens is that index of refraction that we talked about is also a little bit dependent on the wavelength of the material, or of the light, or of the frequency of the light. And so what we find is that lower energies are refracted less, have a lower index of refraction than higher energy light, or kind of smaller wavelength light. And so the violet gets bent more than the red does as it passes through the prism. And because those are bent at different angles, they separate and are what we call dispersed. One, other than light going through a prism, this is also how rainbows work. So in a rainbow, you have the sunlight, white light coming in, and it gets refracted as it enters the water, right? Going from air to water, going from a faster material to a slow material. And so the red and violet are bent differently. They strike at an angle greater than the critical angle, so it's reflected rather than coming out the back end here, and then refracted again as it comes out. And because each one is bent slightly different, we end up with this pattern where all of a sudden there's this dispersion, and red on the bottom and violet on the top from the light coming through the water. And so when you put a bunch of water together, the effect now becomes something like this, where each droplet of water is going to reflect and refract light. And you'll notice, the colors that I showed you before were actually kind of opposite of a rainbow, right? With the rainbow, red's on top, violet's on the bottom. But what I showed you in that last picture, right, was that red was on the bottom, violet was on the top, so actually reverse. Turns out what's happening is that the sunlight that's hitting water higher up in the air, you're seeing the red light from there, the one that's been refracted more, and you don't get the violet from raindrops in that particular area. Whereas lower raindrops, you're getting that violet light, but the red light is being refracted to the ground in front of you. And so this is where you get kind of that order from going red, orange, yellow, green, blue, indigo, violet that we normally see in a rainbow from top to bottom. And so it's because of that dispersion of the light within the water that we see that. The other thing we can see is that in order to see a rainbow, sort of the orientation of everything has to be right. In other words, the sun has to be behind you and the water in front of you when you're looking at it.